types of matrices, we are going to cover, or we are going to study those matrices which are specifically used in machine learning or data science applications, or the types of matrices which you may require to be declared and used in all further applications, right? So we will go ahead and we will see what types of those matrices are and how you will define those matrices in Python. So number one is a triangular matrix. Okay. The first matrix is a triangular matrix, and if you are able to recall it, so can you define what is a triangular matrix is? Okay, fine. So we will go ahead and see what is a triangular matrix. So in case of a triangular matrix definition, if you want to define a triangular matrix using Python, the NumPy will have a function called TRIL, that is triangular. TRI is for the triangular. Okay. So this first three letters, right? Okay. So many of you are now started giving an answer for a triangular matrix. Square matrix is for triangular if entries above the diagonal are 0. There are two types of triangular matrix, lower and upper, and according to it, you have a definition. If the lower triangular elements are 0, it's upper triangular matrix. If upper triangular elements are 0, it's a lower triangular matrix. Okay. So you will see here now an example. So first declaration. Now we will have a two declaration, or we have a two different methods to define lower triangular matrix and upper triangular matrix. Okay. And now you'll remember this TRI. This is for the triangular. Okay. And L represent is the lower triangular. Similarly, for the second function, TRI is a triangular and U denotes is an upper triangle, right? So what you can have is we can create a matrix, and then by applying this function explicitly, I'm repeating it, we'll create a matrix, and then after applying this particular function explicitly, we will convert it into the lower triangular or upper triangle. So now we'll have here a matrix defined as matrix M with 3 rows and 3 columns. Okay. Each row contains 1, 2, 3, 1, 2, 3, and 1, 2, 3. One thing you will have to note here, the triangular matrix is always a square matrix. Okay. Triangle matrix square matrix. What is meant by square matrix? That is number of rows equals to number of columns. Right? Okay. If there are 3 rows, then there must be 3 columns. If there are 2 rows, there must be 2 rows, 2 columns, okay, and so on. And hence, we see here, when we define this matrix M, then we have the same number of rows and same number of columns. That means there are 3 rows, 1, 2, and 3. And exactly there are 3 columns, 1, 2, and 3. Okay. So I'll print here matrix M, and I'll print Now, is that clear up to this? Okay. This many instructions we have used multiple times. So I hope there is no doubt in this. So we will go ahead and we'll see this first operation. What is the first operation? First operation is converting matrix M into the lower triangular matrix. Okay. And we have assigned that matrix name as a lower. Okay, what is lower here? Lower is the name of a matrix, which is equals to TRI, that is triangular, and which triangular? L. L represent for lower. So triangular lower on M. What it will do then? What is the definition of a lower triangular matrix? Which elements are zero and which elements are non-zero in lower triangular? Can anyone tell me? See, Nidhi, okay, listen here. Lower triangular matrix is a matrix where the non-zero elements are present in the lower side of a diagonal. That's why it is a lower triangular. And above triangular are zero. Okay. I'm again repeating it. How to remember it? Lower triangular matrix means what? All elements, non-zero elements are present on the lower side of a main diagonal. And zero elements are above the triangle. In case of an upper triangular, all non-zero elements are on upper side of a main diagonal. Right? So what this particular function is going to do, it wants to convert this matrix M into the lower triangular, and hence what it will do, this upper elements, it is going to make it then 0. Okay? This 1, 2, 3, this 2, 3 and 3. 1, 2, 3. Okay, this elements, it will make them 0. It will convert them 0. Okay. Similarly, we will have second operation, that is upper. And for second operation, you apply, that is TRI, triangular U, that is the upper. I'll first of all write here a heading so that we can differentiate it. Okay. So you will have first a lower triangular matrix and then you have upper triangular matrix. Okay. So in case of first, we have stored the result in variable lower, and for the second, we have stored the result in upper. We'll execute this and we'll see the result. So this is my original matrix, and the size is 3 rows and 3 columns. Okay. If number of rows are equal to number of columns, if this two dimensions are exactly same, then this is a square matrix. Okay. And always remember that upper triangular and lower triangular function, that is this triangular lower and triangular upper. This two function will only be applied to a square matrix. Right? So when you will get an error about the matrix dimensions are not equal, that is dimension 0 and dimension 1 are not equal, when you apply the two function triangular lower and upper, that means you have considered a non-scalar matrix wherein we cannot apply this triangular matrix operation, right? So as a programmer, you have to ensure this. You will have to always take care of a good coding. Okay, good coding will avoid at least a semantic errors, right? So there is a no syntactical error. Syntax is correct, but semantic says that the size of a matrix should be a scalar matrix when you provide this function, and that we will have to ensure. So we have ensured that we are providing a scalar matrix to this functions triangular lower and upper. Now I'll see the result of a triangular lower. See what has happened in the lower triangular. All non-zero elements are present below the main diagonal. This is the main diagonal. 1, 2, 3. This is the diagonal element. And upper elements are made 0. Similarly, for upper triangular, these upper elements are kept and lower elements are converted to 0. This is how you will convert your matrix, given matrix, into the lower triangular and upper. I hope it is clear to you all that how you will convert a given matrix into a lower triangular and the upper triangular. Right? And this kind of operation you will need when you are going to perform a matrix decomposition, and that is required frequently. That is required to do frequently when you work on convolutional neural network, when you work on RNN, that is recurrent neural network, right? So all deep learning operations are like they very much use the concept of matrices. Deep neural networks, they use this operations in many places. When you want to have a decomposition of a matrix, the trace of a having a different types of traces, and that we'll see in the next coming example. Then tensors, how we define a tensor, and all this many examples. Okay. So then I hope it is clear for you a triangular matrix. Then we will have a diagonal matrix. So if anybody knows the definition of a diagonal matrix, then they can tell me, and then we'll see through example what is meant by a diagonal matrix is. Okay, correct. Diagonal matrix definition is very correct, and all of you know this diagonal element. So I don't have any difficulty to convince you all that diagonal elements, or diagonal matrix, is a matrix which have only diagonal elements as non-zero and all other elements are 0, right? So say for example, in this particular case, if you want to convert this matrix into a diagonal matrix, then what you will do? You will make this upper and lower both elements as 0 and only 1, 2 and 3. This diagonal place elements will be kept. Okay. So we'll see through this example. We'll have again the same matrix. Again, diagonal matrix is again applied to a scalar diagonal function. So this DIAG, this is a diagonal function, and it is again applied to a square matrix. And hence, I have not said to define a matrix. I have said specifically to define a square matrix only. So if you take a non-square matrix, then you will get an error that this function diagonal is not applied to that matrix. So this matrix M will have 3 rows and 3 columns, and we applied and extracted diagonal vector from this matrix. Okay. So it is little bit operation which is not directly giving you a matrix diagonal. What we have done is we have first of all fetched diagonal over here, and we have displayed print D as a diagonal of M. And then we have again applied D is equals to diagonal D to create a diagonal matrix from a vector. Right? So we'll go and execute this, and then we'll understand that how actually the results are extracted. Okay. So just have patience and just go one by one, line by line, understand that what is actually happening and how the diagonal matrix is being created. Okay. Well, right here, what we are displaying the result. First of all, we are displaying a matrix M. Then we are displaying that is diagonal vector. after that, we are displaying so first display an entire matrix, second display a diagonal vector which we have extracted, and the next print a diagonal matrix. Okay, so we'll execute this and we'll see what a Python is going to do through all these operations. So this is my matrix M. There is no doubt in this that we declare the matrix with 3 rows and 3 columns and we got this output. Then we will have what we have applied a function DIAG diagonal on M. What this function is did? This function has only extracted. Just consider this operation. Okay. What Dij function has done for this particular matrix M, when you apply it on matrix M, it will be going to extract all diagonal elements, and diagonal elements are 1, 2, 3. Right? So hence diagonal elements got extracted from this matrix M and they are assigned to this D. Now D is my 1D array wherein only diagonal elements are stored. Right? Then after that we have again applied to convert that diagonal element or to create a diagonal matrix from this diagonal vector D. So we will have here the output displayed 1 0 0 0 1 2 0 and 0 0 3. Right? So you will remember that there are 2 steps required when you want to convert a matrix into a diagonal matrix. Number 1 is you will have to explicitly extract this diagonal vector. What you have to do? You have to first extract or take out all the diagonal elements. And after that, you want to provide those diagonal elements again to the diagonal function. And then you will have a diagonal matrix ready. Okay. So I hope this is clear to you all that how we are going to have a diagonal matrix. Diagonal matrix have a very important operations to be carried out in case of a CNN, RNN or any deep learning methodologies wherein a diagonal may represent some specific features. Okay, so if diagonal is representing a very important features and want to perform some operations specifically only on the diagonal elements, then in that case you will have to extract the diagonal, create a diagonal matrix and then apply those functions. There is a question from Shreyas and that is very good. We can do that. I'll execute what Shreyas is trying to say. Shreyas is trying to apply a function like this. I'll take here another variable, say D2. Then I'll do here print what we have done here exactly, we have applied this operation first on M and then second on D. So when you apply this first operation on M, you will get D here and then you apply this second operation. And you execute this, you will get the same result. So that is nothing but the same. I actually have not done this complicated operation so that by splitting this operation, you can understand it very clearly. And once you understand this, what we are going to do is, then you can combine these 2 operations together like this one. Right? So this line and these 2 lines will have the same meaning. Here we explicitly perform these 2 operations separately. That is first extract the diagonal and then create diagonal. Similarly, we did it together here. That is the first innermost operation, the operation which we have performed in an inner bracket, it says that first extract the diagonal from M, and what result you will get here, a diagonal extracted from N, we will apply a function diagonal which will convert this extracted diagonal into a diagonal matrix and assign to D2. Right? So both of these operations are exactly same. I hope it is clear to you, and then we will go ahead and we'll see the next operation. Next is an identity matrix. Okay. So identity matrix is a very, very important matrix in the entire matrix chapter. Okay. And I hope that all of you know what is meant by identity matrix is. What is identity matrix? All diagonal elements have value 1 and non-diagonal elements are 0. It's an identity matrix. And identity matrix plays a very, very important role on, in many matrix operations to study the matrix behaviors, right? And it is also used in many deep learning applications when you want to see some transformation of features. Right? So identity matrix is basically a diagonal matrix with a special case of having all diagonal elements of value 1. Right? So you see how the identity matrix is defined by using Python. So what we did is here we have imported a function called identity. So for defining an identity matrix, we have to use a function called identity. And this is a variable name. I is what? I just a variable name, which is equals to I'm going to provide identity 3. So what is this 3 means? 3 indicates here the dimension of rows and columns. So identity matrix number 1 is a scalar matrix. Okay. Number 2, it is a matrix. Right? So by definition, if it's a scalar matrix, right? By definition of an identity matrix, if it's a scalar matrix, which clearly says that number of rows are equal to the number of columns. And hence, by this definition, when I want to define an identity matrix, instead of specifying number of rows and number of columns multiple times, this identity matrix function will take only one value. Either you specify the rows or the columns and both have the same value, and hence the value 3 indicates that the identity matrix will be of size 3 rows and 3 columns. Okay. So I'll print here the identity matrix and you can see it is 1.0, 0.0, 0.0, that is all other elements are 0 and only diagonal elements are 1. Similarly, if you try to print, create an identity matrix of size 4 by 4. So you will have to be here. It's having 4 rows and 4 columns. For 5, you will have to take here 5. It's a scalar matrix, so it will have exactly 5 rows and 5 columns. This is how you will create a identity matrix using Python. Okay. Hope it is clear to you all that the concept of diagonal matrix and the concept of identity matrix, which is a special case of diagonal matrix. Right? I hope there is no question, and then we will go to the next topic. Right? So next topic is an orthogonal matrix. Orthogonal matrix is used again in many operations of matrix decompositions, and also to have defined different eigenvalues, eigenvectors, and related operations. Okay. So if any one of you know the orthogonal matrix, you can tell me. Otherwise, just listen here carefully. What is meant by orthogonal matrix is? Orthogonal matrix, it is a collection of orthogonal vectors represented by the rows and columns of a matrix. Okay. So note down what is an orthogonal matrix is. Orthogonal matrix is a collection of the orthogonal vectors. Right? And what is meant by orthogonal vector? Orthogonal vector is a vector whose magnitude is 0. Okay. So by this definition, we will define a orthogonal matrix. Yeah, Bansi has defined orthogonal matrix as a matrix. If you multiply with its transpose, the result is identity. That's very good. Okay, that is again a definition of an orthogonal matrix. That means, as I say, one definition is a matrix which is a collection of orthogonal vectors. The second definition says that orthogonal matrix is a matrix. If we multiply that matrix with its transpose, then you will get an identity matrix. That is very correct. Okay, so both the definitions are correct, and we will see the orthogonal matrix. Okay. So we have imported a function array, and then by using this LIN ALG, what is this? It is linear algebra. Okay, this particular library is under NumPy, which says it is linear algebra library. From this linear algebra library, we are imported function INV. Okay. And we start defining an orthogonal matrix as, see here, I define a Q is equals to an array 1, 0, 0, minus 1. Okay. And see here, if this matrix is having row 1 and row 2, or we can say column 1 and column 2. Each of its row or column are representing a vector itself. So this is one vector, this is another vector. Okay. If you try to calculate the magnitude, it returns you 1. Okay. Now we will display, we are actually on the first line displaying it as it is, that is print matrix Q. After that, what we are going to do is, we are going to inverse equivalence. Okay, that means V, see, I have defined it as a new matrix, that is V is equals to INV, the function which I have imported from linear algebra library. So INV I have applied on Q, and what I did is I displayed these two operations. Okay, I'll tell you on the next line what these two different operations means actually. But just concentrate here what we are displaying, and I'll explicitly write over here what has been there in the output, what we are displaying in the output. I'll write the operation itself. First, we are displaying this operation, and then next, we are displaying the operation, this one. Okay, I written it in the double quotation, so it is going to display it as it is. Then we are fine to have an identity equivalence. That is, we are going to multiply this q dot t. Actually, I actually wanted to tell you on the next line, but now we have used this q dot t here. So I will tell you what this q dot t is going to do. Q dot t is going to actually find transpose of q. Okay? It is going to find a transpose of q. So any matrix, listen here, what I'm asking you, there is a question for you all. What I'm asking, if a matrix is multiplied with its transpose, right? If a matrix is multiplied with its transpose, then according to a definition, as I dictated to you by 1C, it says that orthogonal matrix, when you multiply with its transpose, will result into an identity matrix, right? So by this definition, if we have a matrix to define over here, and we try to multiply a matrix with its transpose, and if you get identity matrix I here, then we can conclude that, then we can conclude from this particular result that Q is an orthogonal matrix. Okay, so matrix Q is an orthogonal matrix. So we will execute this and we will see the output. Number one is matrix Q is defined 1, 0, 0, 1. And after transposing, we have matrix Q is 1, 0, 0, 1. Okay, that is 1, 0, 0 minus first row, first column, 0 minus 1. Right? Then second is, I have said INV, inverse. So it has converted the matrix into a floating point and it have again performed the same operation as the transpose has done. Right? This I wanted to tell you actually from these two results, that to find a transpose of a matrix, there are two different ways, but these two operations are going to do an exactly same operation. What is this? Number one is INV. This is going to do an inverse equivalence of a matrix. Okay, and this is going to do a transpose of a matrix. But okay, but in the result, if you observe two differentiations, number one is when you apply a transpose operation, it will just invert this first row, that is 1, 0 is represented as 1, 0. This second row is represented as second column, 0 minus 1, that is 0 minus 1. Actually, in this particular case, the matrix Q and its transpose is exactly similar, and hence you may not be able to differentiate it. But this is a matrix Q originally, and this is a matrix Q dot T, that is its transpose. Right? And what has happened in INVQ? It has inverted the operation. Okay? That is, it has applied the minus 1 on the row wise. Okay? And when you apply this identity operation, that is Q, I'll display on here the operation which we have performed, that is print. Right? So this is an operation, that is matrix Q multiplied with Q dot T as an identity operation. Now all of you please listen for 1 minute, that actually for an orthogonal matrix, okay, in some cases I just wanted to know that when a data has been provided to me, or when I can say I have a good image and whether that image is an inverted image of an original image or not. In that case, what I will do is I will take a matrix original, I'll take a second matrix which I may assume that it's an inverted one, and then I'll multiply these two matrices and I'll find out the result. If result is an identity matrix, then I'll conclude that the matrix or the another matrix is an orthogonal matrix. Okay, the matrix which is provided is an orthogonal matrix. So as we have seen in the previous three examples, number one is that is your upper triangular or the triangular matrix. Number two is whether it's a diagonal matrix. And number three, if it's the identity matrix. We actually did is we actually converted that matrices. Okay. However, in the orthogonal matrix, through this example, we have seen that how we can define whether or how we can decide whether the given matrix is an orthogonal matrix or not, right? So that's it for today's lecture. If you have any queries from this lecture, you can keep this. Before starting to tomorrow, we will take the queries from this types of matrices in the next lecture, and then we will see the next topic, right? So thank you all, and we'll end over this today's lecture.